So you don't need to look at this like the recorded video for sure, but I just want to make your own record so that if you want to review later on after your final, you can take a look. So the bottom line is the fundamental theorem calculus. And don't forget, whatever advanced topic of mathematics you learn, everything is based on this, just nothing but this theorem. Meaning that you can always reduce any like the very abstract like the statement of any branches of mathematics. So just towards the just this statement. So but let's just take the following form. So it just says integral from a to b f prime of x dx equals f of b minus f of a. So this like a statement is sort of magic in a sense that if you really like the rigorously write down the definition of the definite integral that you do not need to know for the final purpose, is that it was written very like the messy way. It is actually the so-called series from 1 to n. We take the limit, and it is written as f prime, say a plus. So let me try to write everything out. Something like this times b. It's like such a like the form. If you really write down its mathematical definition, again, I didn't require to know it for the exam purpose. So the magic miracle like the perspective of this like the statement is that if the function is given, say from x equals a to x equals b, and let's just assume for our intuition that this is non-negative, so that we'd like to know this area. Even though this like the graph is the arbitrary like the smooth like the graph, so we are able to compute this guy only we look at the concept of the antiderivative. So once we know antiderivative, of course in this case it's just nothing but y equals f of x, then this theorem tells you that you just need to plug in those two values on the antiderivative that will give you the area. So that this is the magical way, this is the bridge that we can compute very complicated like the series expression in terms of complete like the different like the object, and it's very simple. So that this is computationally like the efficient and it's very handy to really compute and so on. This is so important for sure. So as you already know, we already have one possible generalization. That's we call it by fundamental theorem. Of calculus, still the same, for line integral. You do not need to memorize the statement, but I want you to click the analog, so how we come up with like such a like statement, and we already saw the proof yesterday based on the chain rule. That so we just want to replace f prime by not log f, and the interval to take the integration by the curve. Then the statement was the following. So when we deal with the line integral along this curve of the vector field, which is the gamma, of course, the definition was the following. So as you know, we take the parameterization. So gamma is parameterized by t between a and b, so that we are able to write down this as indeed the one variable integration from a to b, not of f evaluate gamma of t, doctor with gamma prime of t dt. So this was the concrete like the definition of the line integral that you have practiced with the concrete examples. This says that it is just nothing but f evaluate the terminal point minus f evaluate the initial point. So we have this statement. So if you kind of imagine what happens, so in this case, so everything was on the real line, and we just make the line segment passing through from the initial point A to terminal point B. Then we just need to evaluate the function values of the antiderivative between those two boundary points. Whereas now you have a sort of a line on R2, you have a curve passing through gamma A and gamma B. And for each like the point, so you have a vector field. You have a vector field so that there are a bunch of arrows, something like this. And as you can see, the expression of the dot product, so that means that if you have the, say, novel of f at gamma t and gamma prime of t, then we take the dot product, meaning that we take the orthogonal projection. So you know what I mean? Let me just skip to explain further detail. So that's the meaning of this expression by taking the dot product, meaning that so we just look at the quantity in the direction of the gamma prime of t. So it's an infinitesimal direction of the given curve at that point, chosen point t, and we just take the integration among all choices from A to B. This turns out to be just also nothing but the difference of the function value between two boundary points, so that you can see consistency. And of course, we already saw the proof that the proof of this statement was indeed the fundamental theorem calculus of the one variable version. Are you with me up to here? So this was what we reviewed. So what I expect for you is that after the final, you might forget about the computation like the recipe later on. You might need to review it if those really seems necessary for your own like the study. However, you can get the sense of it if you try to remind yourself that what was this statement. Then you just need to go back to here, and it kind of makes sense to you. Then you can just recall what was happening. So what we want to do is, but still you can just see that this is one step generalization. Do you agree with it? So that this was the case that you start from the line segment and you start from the f prime, or so just a single real value of the function, then we have this. But now you have a, instead of line segment, you have a curve. You have a curve, but the phenomena is essentially the same. Kind of. Are you with me? So that what we want to do is we'd like to look at further generalization. So one step further. So in order to understand now new generalization, so that you need to understand the situation. So the interval is one dimensional interval. Even though we didn't define the concept of the dimension, it clicked with your own intuition. And what about the points? So points are zero dimensional boundary. Is that okay with you? So that you take the integral along the one dimension like the interval, then you just look at the zero dimensional like the object, the boundary, and you take the difference. And this phenomena is also coincide in a way that you still look at one dimensional curve. Of course, now you look at in R2, and as you know, you can also extend to the R3 and so on and so on. So still you look at zero dimensional boundary. It's just a point, just a point. So one step further, you can now kind of imagine that we'd like to increase the one dimension higher. So the integration is taken now, we'd like to take it in two-dimensional surface for integral. And the boundary is now one-dimensional boundary. This is what we'd like to do, so that you can now compare. So first, you need to imagine how that really like to make sense of it. So now let's first like to draw the picture. So the picture would be the following. So if you think about this case, so one dimensional like the curve that we'd like to take the integration along this curve, and there are two like the boundary like the points which are zero dimensional. So in order to make this to be happening, so still let us just draw R2 naively. It can be extended to R3 and Rn and so on, but for our intuition, what should be the two-dimensional surface whose boundary is one-dimensional? We can simply just draw like this. Two-dimensional surface. Does that make sense to you? Two-dimensional surface. Let me call it by D. Then where is the boundary? The boundary. So we cannot have a good color chalk any longer. It's this guy. one-dimensional boundary, which is a loop that we looked yesterday. So what now we'd like to do is we'd like to make such like a statement in this setting. So let me just repeat. We'd like to take the integral now on the two-dimensional surface that is enclosed by the one-dimensional loop. And we'd like to establish the fundamental calculus still. So this statement is called the Green's theorem. Green's theorem. So statement is astonishing. So let me just precisely just give you the statement first, and try to just imagine what this really means. So there is two structure encoded. This is from the boundary. The right-hand side is from the boundary. The left-hand side is the integration taken on the given the target the space. So let me write down the right-hand side first. So the right-hand side is, so if you just write down this the curve gamma, is gamma t. So that if you parameterize from A to B, but as we say this is a curve, we require this. So that let me say, given a closed curve, you can say simply just a loop gamma from A to B. So what we want to do is, and also given a vector field, capital F, and let me use the standard notation from the vector calculus in any of the textbooks. So this is actually related to the differential equation. So let me use just a canonical notation so that later on you can compare. So n comma n. So the x component function is denoted by capital M, y component is capital N. So the right-hand side is written by integral along this curve. Let me say gamma. You can just say this is C, so it's up to you, but you know what I mean. So this is just like a given curve, and you have this. This is our right-hand side. So that you can, if you imagine, how it look like. So you have a close curve, the loop. Over here, this is gamma. So let me say here, gamma A equals gamma A equals gamma B. T is between A and B. So it just rotates like this as a loop, and it just turn or just one like the circle, like a cycle. And you have a vector field, and you know what this is. This is good up to here. But what you'd like to now imagine is you'd like to fill inside. So the concept we'd like to now make is that if you take the integral inside, that becomes the line integral of this like a vector field. Can you imagine what should be this left-hand side? This is now, you need to use your like a brain to really imagine this must be the case. This now becomes, this is sort of the also magic. Double integral along this like a surface. This is now D. And let me write down the full expression. So this is dA, and we already practiced last week that you can use either Cartesian coordinate, say dx dy, and if you change it as a polar coordinate, this becomes r dr d theta, depending on the interpretation and the convenience. So this expression is astonishing. It is written by round dm, round dy, minus round dn, round dx. Let me skip to write the parenthesis and this dA here. And on the final, I don't ask you to even memorize it. I will just provide the formula for you so that you can simply just apply. I want you to just get practice for the from the final. However, I want you to try to understand what this magical statement really meant. So let's try to imagine what this really means. So we have a vector field. This guy is given. So let's try to understand what this is. So if you write this out, Can you imagine with your own intuition what that really represents? What is it? So this M represents the X component, N represents the Y component. So let's naively draw just an XY plane. So you have an XY plane. So this is sort of the information of the M, like the magnitude, and this is the information of the N, like the magnitude. So this corresponds to mx direction, this corresponds to y direction. This is clear. So what is the meaning of the taking the partial derivative with respect to y? So you want to look at the infinitesimal, like the change depending on the y direction. So the first component represents the small amount of the change based on the change of the y direction. Does that make sense to you? This, like the direction, represent round the n, round the y. If you imagine what this is, n represent the y component, y magnitude, and you take the partial derivative with respect to x. So that if you just imagine what this guy means this guy means this guy. We look at the infinitesimal, like the rate of the change, that changes depending on the x change. Can you get that? But now we take the subtraction, so that you should change the direction. So this represents negative round the n, round the x. And now you add them. What is it? Rotation. And the fancy term people usually prefer to call it by the curl. They're the same. So now you can imagine what this expression really means. So the integrand of this double integral represent either the curl or rotation. So that you start from the vector field and you create the rotations on each point and you take order of the summation. That's the meaning of the double integral. Then what happened? So now I want you to get the fancy, like the imagination at this point. So each point, you create the rotation. Can you get that? This rotation for on each point is represented by this expression of the vector field. So if you kind of imagine, if 2 points are very close enough, then because of the same direction, they will cancel each other. Can you kind of get that? So if you kind of imagine how it look like, so if you just make the size fairly small, then for first the rotation should look like this, and this point, this rotation should look like this. So they will cancel each other. Can you get that? I'm just saying everything heuristic, but this is mathematically very rigorously correct. So that what you can imagine, if you try to take all the summation of all those the effect of the rotations, they will cancel each other. All thing left is just the effect of the line integral along the of the vector field. That's the meaning of the vector, the so-called Green's theorem. Can you kind of get that? And the proof is exactly using one the variable fundamental calculus. Yeah, question?
I'm not familiar with the application of especially if we can't explain how hard, but just how would we apply that?
So this is what I'd like to say. So if you just search either from Google or just use GPT, so each of the statement you can find millions of citations for the application in any engineering field. Seriously, so that's why you need to just really diagonally click with the intuition of the statement. Behind the abstraction. Then this could be the very useful in very the different fields. So I just want you to just click, but the philosophical the perspective I want you to see is that why this is sort of the magical the statement, because the mathematical definition of this guy is kind of crazy. So you really need to deal with the power series expression to know this value. In general, this is almost impossible. This is at least cost in handy for sure. However, this the theorem tells you that as long as you know the antiderivative, some the magical function, then you just need to take just a difference. That's it. Then you know the exact the value of the integration, which actually requires to compute infinitely many summations of the values when you just proceed a certain algorithm to really know certain the quantity you'd like to know. And this is a one step further for the generalization. But if you now increase the one dimension higher, then now the observation is sort of really astonishing in a sense that we just try to collect all possible like the rotations inside, which is close by some of the close like the loop, close curve. Then they will all cancel each other. All thing left is just the line integral of this vector. Is that kind of okay with you? This is so even though the name is green, I really do not know who really first observed this funny observation. This is astonishing. But we have one more step today, because I should finish the or scope of the final by tomorrow to give you the review on Thursday. So still there's one more statement. This is called the divergence theorem. So any questions or comments? Is it kind of like a rewarding for you in a way that you spend around just a month, truth be told, but you actually learn very fancy. You start from the vector space operation, which is very basic, but now you have really fancy, like the materials. And trust me, so whatever the subjects in engineering you learn, you can always reduce to either of the theorem eventually. Or those the abstractions are based on the certain quantity. In order to know the quantity, you need to take the integral. In order to compute the integral the quantity, you should rely on those the theorems, essentially. So that this is the way to study mathematics in the concrete way, that if there's some very abstract statement, you have no idea what the heck was going on there, then try to just reduce a setting to apply those theorems, and you can click on it, what was really happening. And you can exactly confirm the values as well. So now you kind of make the reasonable guess. So still we'd like to have one step further. Do you agree? One step further. Then let's just really look at our the observations. One-dimensional interval, zero-dimensional boundary. One-dimensional curve, zero-dimensional boundary. Two-dimensional surface whose boundary is one-dimensional loop. What should be the next step?
Two-dimensional surface for a curve.
Yeah, two-dimensional boundary whose interior is a three-dimensional object. That's the next step. So now you have three dimensions. Let me say just a surface space whose boundary is two-dimensional boundary. Does that make sense, Steve? So we'd like to increase the dimension one step higher. And this is sort of our best thing to do, because our the physical the space is, of course we can consider the time the axis for sure, but if we just take the classical the point of view of the classical mechanics, and we live in the three-dimensional space. So for example, so if you imagine the picture, let me draw one picture so that you can kind of imagine. So let me start from R3. So what you now need to make compared to this case is, now this was the case that the loop was the boundary. Now you should make two-dimensional object as a boundary. So for that, let me just look at the two-dimensional sphere. I'm just talking about the surface. Okay, so sphere just means that, so if you look at x, y, z, so as a vector, so the magnitude equals 1. So just look at the surface. Can you now regard this as a boundary of the inside? So now you have a three-dimensional ball inside. Does that make sense, Steve? So let me try to repeat. So you start from the one-dimensional the loop for the boundary, then fill inside, that give you the surface. Now you start from the sphere as a boundary. So sphere is kind of intuitively two-dimensional. You agree? Two-dimensional, and you can feel inside. The ball in it. So the three-dimensional ball inside means if you look at each the point, the vector, so its magnitude is now less than 1. So we really need to fill just the inside. That's the meaning. Is that okay with you? Still, it makes sense of it. Then what you can now expect is still we can apply the same theorem. So this is we call the divergence theorem. So the statement is the following. So divergence theorem says that given a three-dimensional space, let me say V, whose boundary S is two-dimensional. And if you feel this is so abstract, just look at the case of the sphere. And we just want to look at such a like the possible like the classes. Does that kind of make sense to you? It's kind of the heuristic, and this is also still very example for sure. So now what we should do is the following. So this is now a little bit heavy, but trust me, for the final it should be very easy. I will not ask you any heavy computation in a way that we just had just 1 month to learn. I just want to get your own like the taste about each like the important like, statement before we finish like this important like, class of the multivariable calculus. So in terms of the computation of the quiz today, it's very easy, but let me just still give it a general like a statement. So also given a vector field F, but now it consists of 3 components in a way that we'd like to draw the vector field in R3. So that let me just say this is now denoted by F1, F2, F3. I don't think there's a standard notation of it, so let me just put the natural like indices. So this theorem says the following. So still it consists of 2 different like the pieces. The right-hand side consists of the boundary integral. The left-hand side consists of the interior integral. So this part should be still double integral. Still double integral. So it says this is just nothing but f. Let me use very fancy notation. So f dot ds. And truth be told, in order to really make sense of this notation, I at least need to spend a week. But trust me, in terms of computation, this becomes very easy for our like a class. But let me try to explain this at least naively. So this is same as the triple integral on this like the 3-dimensional space V, and it's kind of not crazy. So we'd like to take the integration on each like the volume, so that's why we say dV. This is not 3-dimensional. You can kind of assume this is just nothing but dx, dy, dz. So the inside matters. This inside matters. So, and this is a definition of the so-called divergence. So let me just put divergence of f. This is a full statement. Again, you don't have to memorize it for the final purpose. I will just provide our statement for you so that you can simply just apply on the final. But I want you to just think about the meaning of it for your own study purpose. So now let me just try to explain what this each of the like the side really represent. So for the right-hand side, especially there's a dot product which looks very fancy. So I need to explain what this is. So right-hand side just means the following. So if you look at the sphere, then what you have is for each point, what can you do? You know how to create the tangent space. Remember that? Equation of the tangent space. We learn it so that you are able to create the tangent space. So as long as you have an equation of the plane, what do you know? You know the normal vector. You always admit the normal direction from the plane. Are you with me? So that you always have the normal direction. Let me say n. So normal direction is clearly just orthogonal to the given plane, for sure, and you know how to determine it concretely. Once the parameterization of the sphere is concretely given, then you have a vector field. Which is arbitrary direction on each point. So each point, you have a vector field. That we have no idea. So this is just a given like the vector field, which is arbitrary one, independent to the given like the surface in some way. So what we can do is you just take the dot product between these two. So that given vector field, take the dot product with the normal direction, meaning that you just look at the magnitude coming from the normal direction. So the left-hand side just really represent this just means nothing but f dot n dA. This is the meaning. So let me try to explain intuitively. So for each like the vector field, so on each like the tangent space, you look at the normal direction, and take the dot product, meaning that you take the orthogonal projection on each vector field to the direction of the normal like the vector field. Then you just take the all summations on this like a sphere. We just collect all those like the as just values as one quantity. That's the meaning of the right hand side. This kind of abstract, I know it, but still I want you to get the experience of this like the abstraction, as this is important. What about the left hand side? Left hand side means the following. So now I need to explain what is the divergence. Can you imagine what the divergence should be? So if you just reimagine.
Anything going towards 0?
It's related. So, but let me try to connect with this observation. So what you understood, I believe, is that if you just take the summation of all rotations, they will cancel each other inside. Eventually, it only left the line integral along this like the vector field. I mean, the line integral of the like the curve on this like a vector field. That's what we know. Divergence of F has the same intuition. So this is very easy. What is it? So if you imagine the three-dimensional cube, and for each point inside of the ball, I'm talking about the inside of the sphere, then you have a F1, you have F2, and you have F3 for each point. And what's the meaning of it? We just look at all each infinitesimal like, changes and take the summation. So this is sort of the blowing up from the bomb at each point, and we just want to detect the sort of the source of it, of the given vector field. So given a vector field, we just look at the source of the blowing up and take the R summation of it. So that just take R effect of blowing up dx dy dz. That's the meaning of the left-hand side. So let me now try to explain naively, so that you start from the inside. You start from the inside, and you try to detect all possible like the effect of the blowing up in it, and just try to measure all of it. And it just turns out to just get the like the flux that you have each like the vector field, and just look at each like the quantity in the direction of the normal vector, and just collect all of it. That's the surface integral, and that must be the same. Prove one-dimensional FTC. So actually, they are all essentially the same. I'm not talking about an analog. I'm talking about the amount of the information exactly reduced to the one-dimensional fundamental calculus. So this was one of the important goals that you should learn from this class of the multivariable calculus. So that now you can see how the multivariable like the gradient and the rotation and sort of the fancy concept of the divergence are all closely related to the one variable fundamental theorem calculus. So what should be the style of the final exam? You need to just practice each of the statement to apply. That's it. Any questions? Mm-hmm.
I thought for finding curl it was the cross product between del and whatever f you have.
You're right. You're right. So there's actually one like the step. I try to make it to be concrete enough in a sense that if you write down, so what you said is, so in fact, I can just choose this like the area, not inside of the R2, but in R3. In that case, I should really use the cross product to describe this like the interior unit.
That works for R2, but not R3.
Yeah, but this is in R2, so this just becomes a scalar value function. But if you just assume the surface is in R3, this becomes a vector field, and it just requires an additional like the test to generalize it. But I don't want to do that. Yeah. But this already address or essentially like the information that you can get the intuition.
For the LHS, that one for finding the centroid, or
I mean, for the finer?
like no, like because you're saying it's like, is that finding the centroid of the object, or?
There could be lots of possible interpretation, but my own understanding is that for each like the point inside of the sphere, so if for each point of the three-dimensional like a ball, we just collect all these like the quantities here, or these quantities here, and just try to measure all those like the quantities by taking the integral. Then it just turns out that so we just look at the corresponding vector field in the direction of the normal vector, and just take all those quantities from the just the boundary. So the or effect of the inside blowing up should be the same as the or like the possible like the outer flux, and take the just a summation. That's the good of the meaning. But there could be lots of other possible and meaningful interpretation. Any other questions or comments? So, no. All right, then let me stop to record.